All right, welcome to the solutions to the 4.2 activity on the definite integral. The first problem says use geometry to evaluate the following definite integrals. Okay, so here's something that I think gets lost. We're going to touch the surface of integration here in Math 141, and then in Math 142, if you press on to Calculus 2, you're going to get a whole bunch of integration techniques that you have to use. But I think what gets lost for students is we get kind of rote in just trying to calculate these things, and we forget that what we're asking for is areas. So we can always solve, not always, we can sometimes solve integration problems by just thinking about what the area is that's represented. So that's what I wanted you to see here in this first problem. So the first problem says use geometry to evaluate the following definite integrals. The integral from a to b of the constant function 4. Okay, we can restate that as the area under the constant function 4 on the interval from a to b. So that's this area right in here. It's just a rectangle. It's a rectangle with height 4 and width b minus a. So its area is 4 times b minus a. Same thing, if we change the 4 to any constant, we're just finding the area of a rectangle, which we know how to find. It's whatever that value constant is times b minus a. Okay, here's a different one. It's the integral from a to b of the line x dx. All right, I've drawn a and b very specifically as both positive. And I found this integral as the difference of the area of two right triangles. So the first right triangle I looked at was this big one. It has base and height b, and so its area is 1/2 b times b. And then I need to take away the piece of it that isn't part of the area that I want, which is this little right triangle. That's right there. It has base a and height a. And so I get b squared minus b squared over 2 minus a squared over 2, or 1/2 b squared minus a squared. If you did that, awesome. That's great. You may have found it with a rectangle and a triangle and added them together. You should get to the same spot. There's multiple ways to tackle this one. But I want you to do one more thing. Move a to the left-hand side. Move a over here, and then show that this still holds. And keep in mind that this area would be seen as negative if you do that. Because the definite integral gives a signed area, it's an area between the curve and the x-axis, so anything that's below is treated as negative. Okay, next one is the integral from 0 to 4 of the square root of 16 minus x squared. This is a function that we won't be able to integrate until we get the idea of trig substitution in Math 142. So we're a ways away from being able to handle this integral, but we can handle it just with geometry. So what does that function look like? It's a half circle between -4, 0 and 4, 0. And we've asked for the area on 0 to 4. So that means we've just asked for this area right here. Well, that is actually that area. This is not a good circle. But that area is 1/4 of a circle that has radius 4. So it's 1/4 pi times 4 squared, which is 4 pi units squared. All right, here is the one problem that asks you to tackle this using Riemann sums, the right-hand sum in particular. And so we want the definite integral from 0 to 2 of 2x minus x cubed. All right, so what do we need to get our hands on? Delta x, it's 2 minus 0 over n, or 2 over n. Looks just like the example from the introduction. So x sub I is a plus I delta x. Well, a is being played by 0, and delta x is being played by 2 over n, so x sub I is 2i over n. And then we remember that Rn is the sum from I equals 1 to n of f of x sub I times delta x. Okay, so we might do some algebra to evaluate f of x sub I first. So we get 2 times 2i over n minus 2i over n cubed. See if I did the algebra right this time. 4i over n minus 8i cubed over n cubed. That looks good. All right, so then we want the limit as n tends to infinity of that sum. All right, if you wanted to just tackle this thing first and then bring the limit in at the end, I'm totally okay with doing that algebra first. I brought the limit notation all along here, but we do need to bring that limit notation back at the end. So let's see, you distribute the 2 over n, you get the sum from I equals 1 to n of 8i over n squared minus 16i cubed over n to the 4th. Break that into two sums, rewrite those as we factor out all terms that don't have the i's in them, so the 8 over n squared and the 16 over n to the 4th. Then we come back up here and we use this sum and this sum this time. Okay. And so that's where we got this and this. Those were from those two sums above. And on a quiz or exam or final exam, those sums will be there if you need them. I'm not expecting you to memorize those. We just do some algebra from there. I did all of the algebra for you on this one. And it looks like we get 8n squared plus 8n over 2n squared minus 16 times n to the fourth plus 2n cubed plus n squared over 4n to the fourth. So again, ratio of leading coefficients. We have squared, squared, fourth, fourth. Leading coefficient in the numerator here is 8 and 2, 16 and 4. So we get 8 halves minus 16 fourths, which is 0. What does that mean? What does that mean? Okay, let's think about what was our function. 2x minus x cubed. 2x minus x cubed on the interval from 0 to 2. So let's see, that's x times 2 minus x squared. So on the interval from 0 to 2, let's see, at 0, what's the output of this function? At 0, it's at 0. At 2, it's at, let's see, 4 minus 4 minus 8, negative 4. 2, negative 4. But it reaches a maximum, or it has a critical value at x equals root 2. Sorry, it has a root at x equals root 2. So here it must hit the x-axis again, which means it must have a critical value in here and do something like this. Not drawn perfectly. I didn't take the derivative to find out where that critical value lives, but what does that mean as a rough sketch of this function? This area and this area must be the same. And those two areas are canceling, and that's why the value of this integral is 0. So this function has equal area above and below the x-axis on the interval from 0 to 2. Okay, so there are the solutions to the activity. See if you can take that to do the homework. That's in section 4.2.